All right, got a lengthy list of questions via email this week. Don't know why you did that. Lengthy list of questions this week via email, and there's some questions up in the chat, but I'm guessing that the questions in the chat here were because of the wrong live stream was clicked on, but I can still do them. So, but let's get to the homework questions first. And so questions, there's actually two homework sets for organic. There is the old and the new material. I'm assuming the questions I got today were for the new material. That would make a lot more sense to me. But anyway, propine can be prepared from 2-propanol. Draw the products of the following reaction to show how this can be answered. Be sure to answer all parts. So the first one you're going to start with, so this is question 12. You've got 2-propanol, isopropanol. This is just your acid catalyzed dehydration, and this will give you propene. Since this is pretty easy, I'll work it out. Next, they're going to do double bromination, so Br2. And this will give you, it'll be a mixture of the RNS forms of this 1,2-dibromopropane. So I don't think it's going to require you to do the stereochemistry for this one. Just call it a hunch. Mostly because the stereochemistry here isn't particularly important to getting the final answer. And then the last step, and it gives you this, is it uses the sodium azide and ammonia mixture. This is step 1. This will get you all the way to the alkyne, but it's going to remove the last hydrogen, so that's why you've got step 2, which is the acidification. And then acidification will put the hydrogen back on the end. So that's 12. 13. Propine can be synthesized, some isopropyl bromide, draw the products. It's actually kind of the same reaction here, just instead they've got bromine. So this is just, and I hate the fact that they're using ethoxide, but whatever, I didn't write it. So this will get you back to the propene, and basically it's just the same one from before. Yep, then they add the bromine, then they add the sodium azide, and that's how you get, it's not azide, what is that compound called? Anyway, the NaNH2. So it's the same thing as step 12, or question 12, just instead of starting with an alcohol, you start with an alkyl halide. Question 16. Draw the structural formula for an alkyne of the formula C8H14 that yields 3-ethylhexane on catalytic hydrogenation. Click the draw structure below. Well, we can start backwards. So we know that we're going to get 3-ethylhexane, so let's draw 3-ethylhexane. This is H2 on PT. Hexane, 1, 2, 3, 4, 5, 6, 1, 2, 3. So the question is it possible to create an alkyne? 3-ethylhexane on catalytic hydrogenation. I can actually think of a few answers to this. So we can't put the triple bond here because any alkyne here is going to require us to have access to basically carbons that don't have, base they can have is one other carbon attached to them. So we can't put a triple bond here, we can't put a triple bond here, but we can definitely put a triple bond here, here, and here. So I see several possibilities here. So let's go with the terminal one. And So let's see what it thinks about that one. I'm willing to bet it gives you a bunch of answers. Oh, ethyl. Not methyl, ethyl. Oh, 1, 2, 3, 4, 5, 6. Sorry, when I drew it with a methyl and not an ethyl. So it tells me that structure is correct. Another possibility, we actually have a few possibilities here. So the possibility is this one here, and another possibility is this one here. So I'm going to check it out really quick to see if it lets me do that. It counts that one correctly. And if I edit that structure, so yeah, it's actually counting all three. So these are all three possibilities. You can do two different terminal alkynes, one on the ethyl branch, one on the propyl branch here, or you can do one that's an internal alkyne. It seems to be counting all of them, so that's fine. But yeah, what I do is I would start with a product, identify where I've got two carbons with at least two hydrogens adjacent to each other. So these two can form an alkyne, and since this alkyl group symmetric, that's kind of a redundant answer. These two can form an alkyne, and then these two at the end can form an alkyne. Question 17. Draw the structure of the major organic product isolated from the reaction of one hexyne with excess hydrogen in the presence of platinum. Click the draw structure. Okay, so hexyne, oh, it's really easy. It's just hexane when you get done. So when it comes to catalytic hydrogenation, we don't get a choice. It's complete hydrogenation. So the only way we can get away without doing complete hydrogenation was something like a Lindlar catalyst, so that you would see PD/C, PD carbonate. There's a lot of different variations of it. But basically, it's a poisoned hydrogenation catalyst. So the reaction of one hexyne with excess hydrogen in the presence of platinum, that's just going to be hexane. (18) Draw the structure of the major organic product isolated from the reaction of one hexyne with hydrogen chloride, one equivalent. So one equivalent HCl means that we only get to do addition once. If we did it with excess HCl, we would definitely get multiple additions. So we've got one hexyne, 1, 2, 3, 4, 5, 6, with one HCl. So your rules here are still going to apply for addition to a double bond. So you're still going to follow Markovnikov addition. So in this case, we're going to get substitution on the substitute carbon. 1, 2, 3, 4, 5, 6. So we'll end up getting 2 chloro, 1 hexene. And we don't have to worry about cis trans here because this is terminal alkene. (23) Draw the structure of the major product isolated from the reaction of 3 hexyne with hydrogen 1 mole of Lindlar palladium. So Lindlar catalyst here is a specialized catalyst designed to only add one equivalent of hydrogen to a double bond. It always results in a cis alkene, and it is cis. We can use that phrase because it's 2 hydrogens that we're adding. So 3 hexyne, 1, 2, 3, 4. It's going to look like that. When we do our HT on PDC or PD carbonate, we're going to end up with the cis form. 6. So again, we're always guaranteed to get the cis form with the H2 PDC. If we didn't want to do the cis form, if we want to get the transform, this is where we get Na, NH3. This goes by a free radical mechanism, and that's what ends up giving us the transform. The following reaction has been described in the chemical literature and proceeds in good yield. The reactant may be more complicated than those you've encountered so far, and nonetheless, on the basis of what you already learned, you should be able to predict the principal product. Draw the principal product for the following reaction. So we have excess NaNH2, NH3, and we have H2O. It is actually a reaction you should already know. The Na NH2, this is a super strong base. The acid workup, the H2O that follows it, is purely meant as a way to acidify the final product because we're going to end up eliminating the terminal hydrogens. So 2, 4, 6. This is hexane. And this is 1, 2, 5, 6 tetrabromo hexane. So we're going to get double elimination there, double elimination there. 4, 5, 6. So we're going to end up getting the 1,5 hexadiene. $35. Draw a stepwise mechanism for the following reaction. We have the alkyne. We have 1 pentyne. First reacting with HBr. This is going to proceed the same way an alkyne does. We're going to do the attack of the hydrogen to the bromide. So that should give us the bromide ion and a very short-lived intermediate. Trouble with this one is going to be drawing the bonds. You have to go from the triple bond to the hydrogen. Oops, didn't put enough carbons in my structure. So now that we've got the carbocation, that's going to take the, well, other way. Arrows in the wrong direction. Bromide's going to attack the carbocation, and that's how we're going to end up with that final product that they've got drawn. $41 and $49. A certain hydrocarbon had the molecular formula CH16H26 and contained 2 triple bonds. Those analysis gave these 2 products as the only products. Draw a reasonable structure for this hydrocarbon and click on the draw structure to draw it. So let's draw out the products. So O's analysis is going to take any triple bond and convert it to a carboxylic acid. And 1, 2, 3, 4. We got then we got 6. 1, 2, 3, 4, 5, 6. So it contained 2 triple bonds and, let's see here, C16H12. This contains 6 carbons. And this contains 1, 2, 3, 4 carbons. And we need a total of 16. So the way to get 16 from 6 and 4, we can have 2 of 6 and 1 4. So 2 of these fragments plus this fragment. And let's see here, if we just do the 6. So it's not possible to do it with 1 6. It's going to require you to have like 3.5 of these or 2.5 of these. So that won't work. And we can't have 3 of these because it'll give us 18. So our only possibility here is we've got 2 fragments that, 2 of these fragments and 1 of these fragments. So basically what happened here, we had these 4 carbons, 2, 3, 4, and they were triple bonded to this carbon with 5 carbons hanging off of it on both ends. So let me do them in different colors. One, 2, 3, 4, 5, 6. So if we have 2 green fragments and this 1 red fragment, we'll get a total of 16 carbons, which is in the chemical formula. So if we attach this to this end and this to this end, because what ozonylysis is going to do is it's going to take any triple bond. So R1, R2, and when we ozonize, we're going to get R1 with the carboxylic acid hanging off the end, and R2 with a carboxylic acid hanging off the end. So if we want to figure out what happened in the reverse, we're just going to pull the OH's, the oxygen of the OH, and we're going to connect this to another carboxylic acid. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we're going to have a triple bond here and a triple bond here. So our total chain here is going to be 16 units long. I'll switch to the desktop, you can see it. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11, 12, 13, 14, 15, 16. So our C6 fragment here, the CH3, CH2 taken 4 times, 4 CH2, that's going to be where our first triple bond is. So 2, 3, 4, 5, 6. Our center fragment contains these 4 carbons, the C, the CH2, the CH2, and the C. So 1, 2, 3, 4. Put the triple bond there, and the remaining fragment here is going to be basically this C6 fragment again. So yeah, the way I approached this, I counted up the carbon in each fragment and figured out how they added up to get 16. And then those carboxylic acids basically represent 1/2 of that triple bond. All right, question 49. Adapt the mechanism for the cleavage of ethers by hydrogen halides to the following reaction. So these are all substitution reactions, and they get really obnoxious because it seems like we forget the Sn1, Sn2 rules, but yeah, whatever. So we're going to start with tetrahydrofuran, THF. And the goal here is to make 1,4-diiodobutane. So first step in this mechanism, we're going to hydrogenate the hydrogen or the oxygen. This just makes it a really good leaving group. Next step is that we get an Sn2 substitution. So we're going to get the iodine to break off that oxygen. That'll leave us with the 4-iodo-1-butanol. And then we're going to follow a very similar mechanism. We're going to add this, and we're going to get the Sn2 pathway to displace the oxygen. So that's all you're really doing with this one, is just kind of walking through it. Oops, wrong arrow. Yeah, I got it. Now, you'll notice it says 65% yield. These reactions are not. You trying to drive this by Sn2 is not the best thing in the world. But that's it. Again, I'm going to guess can you draw the cyclohexane 2D projections was the easiest way to do it. I'm guessing this might be an old post. But just to answer the question, how do you draw cyclohexane 2D projections? You need to define what you think is the first carbon. I prefer to make this carbon number 1, and then I'll start with whatever functional groups are at the top. This is not necessary. There is what's called a C3 symmetry here. So this carbon, and this carbon in this figure are all equivalent. So you could define any of these as 1. But I did actually post videos this semester to kind of help with that question, so please let me know if that video helps. All right, so that's it for questions I've gotten this morning. Again, these are office hours. These aren't lectures or lessons. So you got questions, I've got the chat menu open, and I'll answer any questions that pop up in the chat. Sorry, I missed the second half of that email. So, question about the last reaction on page 14 in the packet. Actually, not as bad as you'd think. So let me draw this monstrosity. 1, 2. So keep in mind, we can get carbon-carbon bond rotation. So what this actually is when it rotates, and I'll just kind of draw it down here, is this. So this is just Diels-Alder. You've got your diene and you've got your alkyne. So let's number the carbons, 1, 2, 3, 4. And we got alpha and beta here. So the symptom of a Diels-Alder with between a diene and an alkyne is the 1,4-cyclohexadiene. So we're going to produce this, carbons 1, 2, 3, 4, and alpha and beta. So carbons 2 and 3 here both contain a methyl group. And then alpha and beta, one's got a propyl group, 1, 2, 3, and the other's got this methyl propyl group. 1, 2, 3. So all this is just Diels-Alders with an alkyne. The difference between an alkyne and an alkene. Alkyne will give you the 1,4-cyclohexadiene. The alkene just gives you the cyclohexene. And 1 and 2 equivalent reactions on page 15 and 16. So with the HCl, we're going to end up getting 2 products, and hopefully I was smart enough to put that in the solution key. Yes. So we've got this monstrosity, and we're going to add HCl to it. And typically, you will get a mixture of both the cis-ins, the trans isomers from what are, yes, you get a mixture of the cis and the trans isomer. The H and the Cl have to be trans each other. But yeah, so the H and the Cl have to be trans each other because they have to be anti-periplanar when they add. It's reverse of Zaitsev rule. Good Lord. Let's turn that off. So the thing is that neither of these are more substituted carbons. So when we add it, 0, 1, 2, 3, I'm going to draw this weird, so we got the alkene here. The only rule here is the H and the Cl have to be opposite each other. Now, we do want to add the Cl to the more substituted carbon, but the thing is both of these are equally substituted carbons. So we could add to either end. We don't have a terminal alkyne here. So we're going to get one where the Cl adds to this first carbon and one where the Cl adds to the second. So that's what the key is showing you is where the H and the Cl are trans to one another. They have to be that way because of how the addition works. But it adds to both. Now, when we add the second equivalent, so that's your first HCl. When we add our second HCl, we now have a more substituted carbon for both cases. So for this one contains a hydrogen and a carbon. This one contains a chlorine and a propyl group. So we add our second equivalent of HCl. It has to go to the one that had the chlorine on it because it's now become the more substituted one. The same thing's true of this one. We're going to have to add that chlorine to the one we already had the chlorine on because that makes it because that made it the more substituted one. I don't see the 2 equivalent in the key, which is weird. So maybe got omitted by accident. Oh, the H2O 2 equivalent. I thought it was asking for the HCl. So for the H2O, this is where it's going to be very different than what we'd expect from alkenes. So when we add water to this molecule, we do actually form this, as a first step, we form what's called an enol. And again, if we were to have if we had an alkene and added our OH group to it, we'd expect addition across the double bond to give us an alcohol. This will give us an enol. So an enol is an alcohol group connected to a double bond. Now, the 2 here doesn't matter. What'll happen on the first equivalent is that we'll start with the enol and then we'll get what's called tautomerization. So what happens with tautomerization is that hydrogen gets picked up by the double bond, and the double bond gets picked up by the oxygen. And so we end up actually getting two ketones in this case. Now again, it's the same reasoning for the HCl, why it goes to both, because they're equally substituted. But that first water that gets added automatically forms a ketone. So that second water there is more meant to actually kind of catalyze the tautomerization reaction. It doesn't actually participate in it doesn't actually get added to the product. But yeah, unlike alkenes, so if we just had an alkene equivalent to this, and we added water, we'd have both possibilities, the OH adding here or here. Now when we add the OH, we initially get a double bond. That double bond tautomerizes and we get a ketone. But knowing me and the reason why it does H2O, one equivalent, let's see the H2O2 equivalents. It's just there to make sure you're paying attention. So there's an H2O1 equivalent as well. Again, it's there to make sure that you're paying attention. Students who aren't paying attention will try to do this. So when they see the two equivalents of the water, they say, oh, you get the diol. So this is not analogous to HCl. HCl will add like an HCl would to an alkene. When we add water, we always end up with a ketone. We can't produce a diol using water and an alkyne. It just doesn't happen. So that's the purpose of those questions, just to kind of make sure that you're paying attention. The first equivalent of water creates these ketones. Adding more water does not change that. You cannot produce a diol directly from an alkyne. This is another reactions we're talking about. All right, so again, if you ever got questions, please feel free to email Advance. Last lab this week for the B group for organic. So y'all are done with labs, and we'll talk about how to get your post labs to me and how we're going to do the post labs for the lab notebooks. Do not forget organic. Unfortunately, our exam is next week, next Wednesday. They're requiring us to do it during the lab time, not during exam week. So we'll talk about that as we get closer as well. But anyway, again, please feel free to email questions or reach out, and I will see y'all tomorrow.